Okay, folks. So thumbs up if you can hear me. Great, thanks. And yeah, thanks for whoever started the recording. We could just get rolling, I guess. So today we're going to talk about classification. Basically, there's a bunch of points on, usually we assume it's Euclidean space, but there are variations to this. And we wanted to put things into buckets or classes. This can be things that we usually eat on their own versus things we usually cook with, or for example, things I like versus things like you like versus those you don't like. And these classes can be a variety of shapes in a feature space that we look at. Well, two brief announcements. Next week on Wednesday, I'm hoping to see hopefully a lot of you in person in physics theater. If you don't know where it is, there's this website called Student VIP that have like an entry and a picture of it. It's not too far from where I'm sitting now, Hannah Neumann. So if you know where the psychology building is, it's around there. It's if you're new to ANU and in-person lectures, this business of in-person lectures, make sure give yourself a bit of time, and we will try to basically deliver the lecture in dual mode. Wish us luck. I will go there and scope out the AV system beforehand. There's that the content of the lecture is one that probably the only one that we'll plan to cover outside of the PRML book. It's called generalization. I'll post some pointers beforehand. Another reminder is quiz 1 is next week. It's open book, open anything, unlimited time, but you get one try. No need to stress. It's supposed to just like warm you up on the like some materials in the first 3 weeks. Yeah, we'll get to that when we are close to the release date. So today we're going to talk about classification, or most people in the popular press knows machine learning. We will talk about the problem, briefly go back to section 1 to review decision theory. Right, Xuyang said, okay, physics T. Right, okay, thanks for that. I will make a note and make sure we do some recording and scope it out. If needed, we might change to another room. Stay tuned. So updates to that will be on Piazza. Right, and then we'll cover 3 basic types of classification models: discriminant functions, generative models, and discriminative models. They have similar words, but they do mean different things, so bear with us. I would say this particular lecture, what I'm hoping to get through to you are a bunch of insights. So it will be basically an interleaved sequence of intuitions and a bit of math. And the math will hopefully give you insights such as why least squares sometimes don't work, and well, we like get our logistic function back again from scratch, which also tells us why there is a probabilistic view of logistic regression as well. Actually, 2. One is the generative model, one is discriminative model. So there is a fair bit of material, but I will, upon popular request, some of you relay some feedback to the tutors, I will pause from time to time. So just remember, there's basically the most switching between math and intuitions. If you get lost in the math, don't worry, you can go back to it again and just stick with us for a while. In case we don't get through all the materials, we can cover it in front of the generalization lecture. All right, so classification, this well illustrated from a classical example on a small machine learning benchmark dataset called IRIS. This is available from the UCI benchmark dataset. So there are 3 types of flowers, IRIS flowers. They're all purple. For a lot of you, you may say, "Oh, yeah, why do I care?" Right? Yeah, plant biologists do care, and this is like baby steps of computer vision system trying to automatically sort things. As you can see, measured in the 2-dimensional space of length of the petal versus sepal, which is this part of the flower. The 3 classes reside in distinct regions, right? But the separation between the blue and green are rather complex. Okay. So how do we represent classes? We've been operating in this realm of target variable t being either 0, like between 0 or 1 for the sinusoid regression problem. For here, this particular book takes the probabilistic view. It seems convenient that we just assign, say, if the target variable is binary, we assign it to be either 0 or 1. Well, this can mean many things, like whether we're meeting in person or remotely, whether a medical diagnosis is benign or malignant, and so on and so forth. Well, you say, what if there are multiple classes? So I guess the key distinction between classification and regression is the target being discrete, as many of you know from either Intro to ML or computer vision or many of these other classes. But in real world, not every problem can be converted to binary classification. In a lot of cases, it is choose one label among many possible labels, such as, well, the iris flower example we covered, and also object classes in photos. You may say there is more than one object in a photo, but for example, in the inception type of the network, each of the output units trained to specialize in one class. And also natural language, what is the next word or token is essentially what's called a one-hot vector among all possible tokens, which can be vocabulary or byte pairing, like subword units and so on. So the key for the one-hot encoding is that there can be only one token that are activated among all the possible dimensions. So sum over t of k is 1 over, we haven't specified the dimension, of course. So if we sum over k over this, there's only one that's active. Okay, so there are other representations possible. It could be non-zero or 1. There's an example in this section of the book that we're not going to cover. You can scale this value to some real value. There are also good reasons when we want to represent these classes as in other numerical forms, such as +1 and -1. This will become handy. Perceptrons, we'll see a little bit of it, SVMs, and also in generalization, where it's easy to analyze. Right. So let's go back to section 1. Because we are essentially observing some measurements. In the iris example, they are real value measurements. And we wanted to essentially make a decision that are among one of many discrete choices. So this calls for some care. Right? When we do, so in this case, in the case of chapter 1, they call inference. Again, the word model and inference are quite overloaded. Let's just say for this particular section, the inference is refers to computing the joint probability between x and t from a set of training data for both vectors. And decision theory refers to taking a specific action based on our understanding of the value t is likely to be. In this case, in the last page, we also said, well, we sometimes call the target variable t classes when they are one of k discrete classes. So this could mean reasoning about the posterior probability of t or class label ck by invoking the Bayes rule, no less. One thing that I think, because it's chapter 1, it oversimplifies by saying, well, I think deliberately, it's not that the author doesn't know, that the decision stage is generally very simple. This is, in a lot of cases, not true. We need to be a bit careful about this, even trivial. So we can, of course, take the maximum a posteriori class label, but this is not necessarily the right decision for a given real-world problem, such as medical tests, tests on quarantine for COVID, or other types of machine learning models that are at the forefront, such as active learning, online learning, RL, ML, machine learning and economics, and so on. So taking action, let's just say, can be non-trivial. Let me pause and ask, can you guys hear the background construction noise? If it doesn't affect you, I'll just keep talking because it's quite loud for me. Unfortunately, my office is overlooking the construction site. Yes, the justice system. Thanks, Vikram. So let's still, well, assuming that caveat, let's still look at, in a simple case, assuming we just have class labels C1 and C2 that are divorced from some real world significance, what should we do, right? So as we said, we care about the joint probability of X and C, or X and target variable T. And we can assume this joint probability to have some general shade. Let's say one of them is unimodal, the other one has 2 bounds. We can actually write out the expression for for the probability of being correct or wrong in this case, assuming we, because X is one-dimensional. Okay, thanks, Luke. Yeah, I'm actually not sure how to tell them, like, we can't tell them to shut up, and I'm not sure if wearing an earphone helps. If it gets bad, we will try the Bluetooth, like AirPod, and see if that helps. Right, so because X is one-dimensional, and we generally want, let's say, our decision regions to be continuous. There are cases where we don't have to have it to be continuous, but for simplicity, let's say we choose a threshold X hat to separate class 1 on the left versus class 2 on the right. And the probability of correct classification is simply that for each class, we look at these regions, decision regions induced by this threshold. So within region 1, we look at what's the joint probability between X and C1 is. And within region 2, we look at what's the joint probability of X and C2. So we integrate over X in the corresponding region. So what's more interesting is the probability of mistake, right? So it's basically, for the 2 class problems, it's basically a cross, right? So when we want to know what the classifier makes a mistake when we are in region 1, but actually it's the X is generated by the joint probability of X and C2. So that corresponds to basically the red and green region here. And the other type of error is when we are in region 2, but the data point is generated by the join with class C1. So this is denoted by the blue region here. as you can intuitively see, given that we determine x hat, this is not the best, right? What's shown here. Because if we move x hat to this direction, the sum of the blue and green region will remain the same, because this is where the two class joint probabilities kind of overlap, but the area under the red region will actually decrease. Right? So we should move this decision threshold. Well, if example, minimizing mistake is the objective, we can move this decision threshold until this red region disappears completely. All right. So that's, I guess, the gist of decision theory 101. And let's just take a brief look at when we don't want to do this. Well, in a lot of machine learning, we still do it, and it's useful in a lot of cases. But let's say take the example of medical diagnosis. Right? So let's say the tests or different patients come in as two types, cancer or normal, for a particular type of cancer, for a particular, say, type of imaging we're looking at. If we misclassify a normal test as cancer, yes, it's bad. The patient will be, or as possibly cancer, the patient will be quite stressed out, but we can run additional tests and monitor the patient over time to see if it's indeed cancer. On the converse, if the true label is cancer, but the machine kind of said, I recommend this to be not cancer. I don't think this cancer. The patient can go home and live their happy life. But if the machine in that case makes a mistake, then the cost is very large. It can be the cost of life, right? So that's not good. Therefore, it prompts, it pays in this case to have asymmetric loss matrix. What it means it is essentially to insert this loss term, pairwise class loss term. Example, if the class was class K and the machine classifies it as class J, what kind of cost does it incur? And then do the same integration as the last page. The decision for, well, the loss sensitive decision is therefore basically this weighted term, including the loss. So another problem with this particular, this particular kind of mistake is that when the two classes are imbalanced, then just computing the sheer probability of loss or mistake, let's say region 1 or class 1 has, let's say, 95% of the population. This is true for, let's say, COVID, where at any given time, hopefully not more than 5% of people have it. Then if I'm just plainly minimizing the number of mistakes, I'm just going to go ahead and classify everyone as not having COVID, which is not good, right? So there are many recipes to address the class imbalance problem. One of which, one of the simple fixes was proposed by Cheng and his co-authors, Cheng Song, who was one of the authors of the MML book, and he also works and lives in Canberra, so I thought it's good to talk about something people close to us do. Their proposal was simply to take an average of the accuracy of each class. And in here, the accuracy refers to what's called a true positive, meaning if we have a two-class problem here, and have a data set, or let's say testing or validation data set, and we can count over basically how many actual cancer classes tests are predicted as cancer. So in this case, 90. So this is a true positive. And the total number of cancer cases in this case is 90 plus 4. So in this case, the cancer record, like the cancer class accuracy, so true positive or positive is 90 over 94. And similarly, the true negative over negative in this case is 5 over 6. Right, so plug in the formula, you can see that this sort of gives a balanced view of both classes, despite in this particular data set, the cancer cases, there's a lot more of it. Right. Another option, so essentially this particular slide encompasses 3 ideas. The third idea is to have a reject option, right? When basically these 2 class posteriors cross, you can say, well, I'm unsure because in this region, I'm prone to make an error anyway. Maybe I should just refrain from making a decision right away and ask for some more data, do some more tests, and so on. With this cartoon picture of decision problems in mind, we can conceptually characterize decision problems, or basically classification problems, as 3 types. The first is finding a discriminant function that maps each input directly into a class label. In this particular case, the discriminant function is basically the threshold. And we can think about these discriminative models that solves for the class, like the probability of the class given input. And then we can use this to assign new x to one for classes. There is also the so-called, generative models. You may think in this particular case it's the roundabout way, right? So I care about class labels as output, but actually I'm going to turn around and model the probability of data given class labels. And I also can incorporate the prior class probabilities. And then I use Bayes' theorem to flip it and then find the posterior probability of the class. We can also model the joint discriminant P of X and CK directly. And then eventually we somehow use decision theory to assign a class label to new X. This is a mouthful, but it gives a lot of flexibility and conceptual clarity, as we will see. So in the rest of this part, we're going to talk about this one first, then this one, and then the discriminative model at last. It's also informative to have a look at figure 1.27 as our concluding thought for chapter 1, 1.5. In this case, we can see that if we care about the generative view, basically probability of X given C, we can capture the multi-model nature of, say, in the first class, right? So it's more expressive in this way. But if we only model the class posterior for the same class conditional densities, we can see that the 2 modes of P of X given C1 has no effect in the posterior ratio, posterior of class given X, simply because in here, due to Bayes' rule, you can see the probability of the second class is too small to really matter. It tells us basically 2 things. We can read it from 2 angles. One is the generative model can be more expressive. The second one is if we only care about making decisions, doing the modeling in discriminative sense could essentially free us from worrying about details that may not be important. All right, so these are like a bunch of philosophical or half philosophical rant about how we go about doing classification. Right? So I like to start from this schematic on the supervised machine learning, which we have been covering, right? So in here we talk about classification. So from the real world, we magically determine what there's a set of variables or measurements we call input. And then we have a task and we try to express it as yi's, right? And we define a model in which include its parametric form, and the parameters are called W. We choose a loss, an objective function called L of W. We have seen that different choices of loss functions can have inherent connections with each other. We will see that again today. And then we do the quote unquote learning. It's basically finding some optimal W, such as maxima posterior of W, or minimizing some loss function, right? So after we've done all of these, we go and use f of W on some new data to make prediction using the optimal W we found. So this should be pretty obvious, except I would say that, well, in this day and age, and since we're talking about medical diagnosis, justice, like giving people credit or not, there is a lot of limitations in this like traditional machine learning worldview. For example, just encoding data has lots of biases and assumptions. And sometimes when, for example, the learning don't work or the generalization don't work, we should ask if our data changed and whether we should go back and change the data. For example, in the iris example, just the two-dimensional measurements are perhaps not enough to simply linearly separate the classes, but if we can take more measurements, we might. Okay, so that's the intro part of what is classification and what are the principles to go about doing it. So let's look at discriminant function next. We've been living and breathing least squares in the last 2 weeks. So we're going to break it today. So a discriminant is a function that maps from an input vector to one of the k classes, denoted by C of k. We first consider two classes. And, well, linear functions are simplest, and we have convinced ourselves that we know how to learn linear functions in regression. So let's do that. So let's say our discriminant function is y of x, and we want x to be assigned to class 1 if y of x is greater than 0, and to class C2 otherwise. So it's parameterized by a weight vector and bias term. And it's also called the minus a negative of the bias term, we can call it threshold because y of x equals 0 matters. It's basically the separating hyperplane, the linear function. All right, this looks familiar. We've been working with this all our time in the last 3 lectures. So the decision boundary is, this hyperplane. And it's just worth noting that W is orthogonal to any vector lying on the the discriminant function to be precise. Right, so the contour lines of y of x are hyperplanes too. So y of x is then the sign distance of point x from the hyperplane. So so here are 3 examples. The first case is W transpose x. Right, in here we assume that, so we don't have the bias term. Right, so in here W is 1, 2. The direction of W is this way. And these are the contour lines signifying y of x, right? So the second example is W is -1, -2. So this is the same as this one, except the signs are flipped. You can see that the sign of W is flipped, and the colored intensity map of y of x, the value of y of x is also flipped. Basically, which because y of x equals 0 is the separating hyperplane. like which one is class 1 or class 0 is flipped. And we can also have W transpose X for W equals 2 and 4. So this is essentially the same hyperplane in the same direction as the first one. But here we just get a longer vector W. And also the values of Y of X is larger, right? So on the same color scale, we can see the colors of Y changes more than the other way around, than in the first example. So you may ask, isn't the first and third one equivalent? The short answer is yes, when we don't have regularization terms for W, and we don't have calibration for Y of X. So if we're doing regression, right, they will correspond to different, the Y of X being scaled by a factor of 2. But if we're doing classification, as we will see in the next few slides, this kind of breaks down. So I'm not going to cover this one. I leave that as reading. I think it's interesting geometric intuitions. So what are possible problems of discriminant functions such as this, right? So basically, Y of X equals W transpose X. I'm going to omit the bias term here. So if we have, let's say, this picture illustrates two problem cases. If we have two classes, but instead of learning one discriminant function, we somehow want to learn two discriminant functions. Or if we have, let's say, 3 classes and we learn 2 discriminant functions, what would happen? In here, if one discriminant function says, well, over here there's a C1, below this hyperplane it's not C1. Right. So this is basically the one versus all scheme. I want to learn the discriminant function for each of these classes. And then the one versus all discriminant function for class 2 is this one. We might think this is enough for classifying 3 classes. Okay, you can see that, well, over here it's class 1, over here is class 2. When it's not class 1 and not class 2, I assign class 3 label to it. But what about here? In here, the 2 discriminant functions are arguing with each other. One of them says it's class 1, the other one of them says it's class 2. Oops, bad news. So in the green region, we don't really know if we only listen to the discriminant functions. So there's another scheme called 1 versus 1. So instead of doing this, how about we learn a Y of X discriminant function that distinguish between each pair of classes, right? Here, C1 versus C3, C1 versus C2, and C2 versus C3. So in here we have essentially n choose 2 number of discriminant functions to learn. There's more stuff to learn to estimate from the same data. And we hope we won't have the same problem, but not quite the same, not quite the case, right? So in this particular example, in the green area, according to this line, it says it's C2, C2. According to this line, it says it's C3. And according to the third line, it says it's C1. So all 3 discriminant functions have like conflicting opinion. Then, well, we can't decide again. This is one drawback of discriminant functions, but luckily there is a fix to this that's actually quite simple. So what we do is, rather than learning, so in here in the last page, so this means, suppose we have k classes, this means k minus 1 discriminant functions. And the other one means like k choose 2, k times k minus 1 over 2 number of discriminant functions. I'm just saying y's, right? But instead of doing that, what we need to do is to simply learn k discriminant functions and then take the max. The reason for doing this is that if we have, let's say, linear functions like this, if we do so, so here is where the notion of convexity again comes in. In here, we're not talking about convex functions. We're talking about convex sets. So here, convex sets are essential regions in their continuous step space that roughly look like this, where if you draw a line segment within the set, the entirety of the line segment falls within the set, right? So, well, if the line segment starts and ends in the set, then the entire line segment is in the set. So here is a non-convex set. It's not called the concave set, right? So the notion of convexity appears like a few times in different manners. So this is one way, right? So if we don't, if we apply this notion of convex sets to the discriminant functions y, and we simply make the decision that C of k is, we assign it as arg x y of k x. Change notation. Say the best class label k star is arg max y k over k, right? We can show that the decision regions are connected and convex by simply invoke the definition of convex functions. Because linear function are convex, we can show that if there are 2 points xa and xb, for which yk of x is the maximum among all discriminant functions, then for any point in the middle, k is also the maximum class label, right? With a linear combination lambda. So firstly express x in x hat in xa and xb with a parameter lambda between 0 and 1, and then if ya is like yk of xa is the largest among other k's, when yk of xb is the largest among other k's, then the combination of them is still larger than the linear combination of any other k, right? So there's that. So we haven't talked about how we estimate these discriminant functions. Since we know least squares, let's see if we can use least squares, right? We just plug in. The y of x looks the same as the regression function. We write it in matrix form with the bias term or threshold term absorbed. And for now, our target variable, as we covered at the beginning of this class, it's let's say 2 classes. So these are like t's, zeros and ones. And this trace term is basically a fancy way of writing linear, least squares. And out comes the normal equation. And pictorially, it looks like this, right? If we have a bunch of red dots and blue dots like this, we fit linear, like minimize linear, like square error, and we get this. So it looks quite reasonable. So what can be a problem with this? Right, so there's a whole bunch of, let me pause and go back a little bit. The orthogonal question, I'm going to, there a way for me to mark it. I'm going to leave it as Q&A at the end. So Vikram, there is no analogy that one discriminant function is more convincing. And here we're just care about which one is bigger. We assume they sit in the same numerical range. So for Qinyu, singly connected region means, we can think of it as like you can make a shape like this on the plate or on the table. When it's not singly connected, like these are not singly connected regions. And by definition, they are not convex, because when there are multiple pieces, if I set the line segment to start in one piece and end the other piece, then there are definitely bits of the line segment that are not covered, right? So that's bad. That's not convex. I hope that helps. Right, Vikram asks, right, is this point special? Are all the regions going to meet at one point? I'm actually not completely sure of the answer, right? So we have a bunch of hyperplanes. I believe it's generally not true for more than 3 classes. So for 3 classes, I don't know an answer on top of my head. Yeah, okay, I'll mark this for later. Let's go back to the least squares in the normal equation that we looked at a lot. So here's a picture on how when least squares break down. Right. So what this does is, what least square does is basically whichever side we call like 1 or 0, but the W vector that's being learned is perpendicular to the hyperplane, and then we assume, because the target variables are 0s and 1s, we assume basically all of these red dots have like a value 1, and all of these blue dots have value 0. We essentially collapse this 2-dimensional feature space into 1 dimension, the dimension of decisions or discriminants, and we say that we want all of the red dots to be around 1, all the blue dots projected on the dimension of W to be around 0s at this point. So why is this? Well, in this particular case, it's engineered. Well, the synthetic data is generated so that it's the case, right? So blue dots are like around the same, right? They were like around this point plus some noises. But classification problems don't look like this, right? So if we're classifying, let's say, cars, there are many different cars that look very different. So for multimodal data, trying to force, say, all of the blue points to lie around the decision hyperplane around with a projection value around 1 is or 0 is not gonna work. So in other words, we would, for good discriminant functions, we want them to separate the classes, but we do not necessarily care about whether some of the correctly classified points, how far away they are from the discrimination boundary. Right? Okay, this like is a lead into a whole bunch of things, including VM and what we talk about later on. But let's just pack that as well. So bad news. This like we cannot use least squares to learn discriminant functions. But how do we do it? So here is a simple way, right? So people know from linear algebra a long time ago that this seemed to break. How about we just clip the discriminant functions, right? So here essentially we have this, let's say, contour lines of y. So w is here, and then y equals 0, y equals -1, y equals +1, let's say, and so on and so forth. And then we just clip it. We assign this warping function where like everything on one side of the decision hyperplane here gets a value of +1. So this is f of yx equals +1, and everything on the negative side f of yx equals -1. So this basically the decision value now is completely flat. I only care about on which side of the boundary you are, how far it is from the boundary. This is called the perceptron algorithm. It was invented by Rosenblatt in 1962, and it's the precursor to neural network and many other cool things afterwards. So what does this mean? It means an essentially error function like this. If I re-encode the target variable as +1 and -1 as well, in here we change the representation, we want essentially the target value and this warped discriminant function to agree. Essentially, they should be both +1s or both -1s. Right. Therefore, we multiply them. So if they agree, then in every single one of these, the product W transpose phi of n is, let's say, a feature vector, and T should be 1. And that's when the sum of products over the data set should be maximized. And we put a minus sign on this, and we want it to. So this minus sign is basically saying this is an error function, E of perceptron with parameterized by W should be minimized. And if you take actually a gradient with respect to, say, so if you take the gradient that only involves the nth data point, like ignore the summation sign, just take the gradient with respect to W, you get essentially, well, these are all linear terms, right? These are data sets fixed. So you essentially get the gradient being the feature times the target. And if we put a scalar, this is our learning rate essentially. In front of it, we get our standard stochastic gradient descent recipe. You may think this is naive, but what this buys us is that, well, there is a perceptron convergence theorem. There's also a perceptron like generalization theorem that will form the basis of a generalization, a lot of other generalization theories. So if there exists an exact solution that we can actually linearly separate the data set. If the training set is linearly separable, then the perceptron learning algorithm, by doing essentially this naive stochastic gradient descent, is guaranteed to find the exact solution in a finite number of steps. So that's encouraging. It's computable. But the bad news is that until convergence is achieved, we will not be able to distinguish between a non-separable problem and one that is simply slow to converge. So algorithmically speaking, that's not so good. We can just keep trying, but we don't know if the data set is not separable. The book has an example of a separable case and illustrates the iterations. I won't go through this here. Ask me a question if you want. I thought, right, so here is the like the culture bit about perceptrons. I wanted to say two things. One thing is Frank Rosenblatt had to implement the perceptron in hardware. And this is what it is. So back in those days, designing a simple model and demonstrating that it works involves real work hardware, rather than right now, if you were to code up a perceptron, it takes you less than an hour to pick up the right commands in either sklearn or torch or one of these. So tools do matter. The second note I wanted to make is that, well, perceptron clearly played an important role in the history of machine learning, as we will see. It looks like a toy model, but it is, conceptually neat, and it's useful for many type of analysis and algorithm design. However, Rosenblatt's work was criticized by Marvin Minsky, again, a pioneer in artificial intelligence. Those of you who have taken or seen computer vision might have heard the story that the entire field of computer vision started when Marvin Minsky gave one of his summer students a task, say, hook up a camera to a computer and see if the computer can recognize images. And it took people like 40 years, 50 years, and that problem is still not solved. Or it's solved somewhat practically, but not generally solved, right? So the book, Marvin Minsky's book, showed that neural networks were consisting of perceptrons at that time were fatally flawed and could only learn solutions for linearly separable problems. This is true for single-layer perceptron networks. And it was merely conjectures incorrectly that they apply to more general network models, which is we now know to be not true, right? Unfortunately, this book contributed to the substantial decline in research funding on neural computing and perceptrons. And the solution that was like a situation of that was not reversed until the mid-1980s. So in the mid-1980s to the early 1990s was another boom for neural networks. So I guess the spirit of this little piece of history is that I guess biased views or misconceptions about a particular model could hinder the progress of the entire field by a lot. And unfortunately, Rosenblatt also passed away at the end of 1960s, and he wasn't able to debunk that. So after the mid-1990s, some of you might remember or have heard that neural network was also went out of, I guess, the then small machine learning community's favor because it was believed to be prone to overfitting. And like the computation power wasn't what they are now. Therefore, right, it sort of went into a quiet mode by the few champions we who now all have Turing awards until they can find and publish and show to the rest of the AI community what neural networks could do. Here's another little bit of a philosophical rant, which is this simplified picture does not take into account, let's say, evaluation metrics that we care about in the data set in a real world task that may or may not like exactly agree with the loss function. It does not have include the thing called validation that we all know, we all do. It also does not cover, say, the implementation layer of the ML algorithms, which may include, like, let's say, cloud ML, drag and drop, your favorite Python and R packages, or cloud support for Python and R, and so on and so forth. Right. Moreover, the interpretation, like what happens when your ML model don't work, or when you try to decide whether what you have estimated works or not. It's this, let me say, cloud of like this operation called interpret and diagnosis. If you're doing a research project, honors project, or the like, master's project, you will necessarily be doing this task whenever you're doing machine learning. And this task will often lead you going back to, let's say, ask questions about learning algorithm, whether it has converged properly, whether you have chosen the right objective or weights, whether you have defined the right models, or even whether you have the right data. So what we have covered so far are classification with discriminant functions and perceptron. Let's now step back to probabilities. I mean, scan if there's new questions. Okay, is f a sigmoid function? No, and deliberately so, because look at the hardware here. This is not a hardware that can differentiate. It's literally like a light bulb or a switch going up when it's +1, and not going up when it's otherwise. I hope that helps. Yes, Yuema said it's just a nonlinear function. It's actually, what should we say? The book is missing a picture. So here's our picture. A. Here is f of a +1 and -1. So, okay, yeah, but I drew the two-dimensional one. The one-dimensional one hopefully helps. All right, time passes by quickly. Let's try and cover the generative models and see how we go. So since we're talking about probabilities, let's, we bet it pays to look at Bayes' theorem again. So there we go. Here's Bayes' theorem for two classes. If we would like to compute the posterior probability of class 1 given x, and there are two classes, we apply Bayes' theorem. The bottom is simply the joint probability of x and z, and c expands to, it's the marginal probability of x, right? And then we expand that using the joint of the two classes. Okay, now we do a manipulation, right? So we define alpha of x as a function of x. That's essentially the ratio of the joint probability of x and class label, which is inspired by these expressions. And we take the log in front. We can actually express this whole term, which looks quite complex, as involving only one symbol alpha. Right. And the function of, well, so basically what we have done on this page is simple manipulations that shows the posterior probability of the class label given an example is the logistic sigmoid function of the ratio of the data likelihood times log ratio of data likelihood times class priors. This is yeah, a manipulation that's interesting. So log and ratios of probabilities are quite useful. Let's see how this will play out and influence what we do. As a reminder, the sigmoid function looks like this. The form is written like this. We can verify that when alpha is 0, it's 0.5. When alpha is positive infinity, it goes to 1. When alpha is negative infinity, it shrinks to 0. And moreover, the slope of this sigmoid function can be adjusted if we put coefficient in front of a multiplier in front of the alpha. And well, it has the symmetry property, right? So what's also interesting is the inverse of this function called logic function. We just, in here we call it alpha as a function of sigma, which is, well, the inverse for function, we simply just turn the coordinate around and stare at sideways, right? So it is the ratio of posterior probabilities. It goes to positive infinity when one of the posterior probabilities is close to 1 and negative infinity round. So this is also called log odds. So goes without saying, you should feel free to use these properties without proving them from scratch, but it's good to convince yourself once, perhaps, the derivative of the sigmoid function is nothing but itself times 1 minus. We'll be using this. So you now say, oh, so we can use the sigmoid function. It's intuitively related to some sort of discriminant, but now we are explicitly modeling class conditional probability of data given class. What about multiple classes? So in this case, it's the solution is simply this multi-class softmax function, where we can define alpha k as not the ratio, but simply the log of the likelihood times the prior. And then the posterior of each class k is the softmax function involving the exponential of alphas. Right, so you could call it soft argmax if we're trying to do classification, but this is less common. So let's model some actual probability. We know a fair bit about Gaussians, so let's just do that. In this page, we're assuming there are, the 4.64 is quite general, but we're assuming 2 classes. C1, curly C1 and curly C2. And then they have the class means are mu1 and mu2. And they have a shared covariance matrix, sigma. That's basically what this equation above is saying the sigma doesn't have a subscript, so it's shared. If we plug in, so from 2 pages ago, we know that the class posterior is nothing but sigma of alpha, and alpha is this expression, log of ratios. We simply plug in this Gaussian class conditional into this ratio, right? We keep the prior, so this ratio term is, when we do the derivation, so we plug in this expression in here, we can see that when we take the log, these different multiplier terms, they fall apart, right? So we can just separate them, which is nice. So if we just take this part, this cancels out because they are the same. This one is also like the ratio, this cancel out. And then we're left with the exp term. In the exponential term, when we take the log, the x log cancels each other. We are left with something like minus a half x minus mu1 transpose inverse x minus mu1. And then minus, well, turns into a plus when it's on the bottom. Half x minus mu2 sigma inverse x minus mu2. There's a transpose in front. So these are, again, 2 quadratic terms. We can see that the quadratic term, so x transpose sigma inverse x transpose x, so this cancels out because they are the same. And the linear term becomes this, because there's a 2 multiplier canceling out the 1.5 in front, and we have like sigma inverse and mu1 minus mu2 as a multiplier for x. Right. And then the constant term that does not involve x comes here, right? So these are the zeroth order term. And we haven't forgotten this ratio of priors. So they didn't disappear and they come here. All right. So what we just did was to show that, hey, if the class conditional distribution are Gaussians, the discriminant or the class posterior probability is a linear function in X followed by a sigma. Right? This looks familiar for those of you, I believe, yeah, more than 3/4 of you who have taken IML will have seen logistic regression. For the rest, even if you have not taken it, you might have heard of it. But we're not doing logistic regression, but logistic regression falls out, which is neat, right? So we're seeing connections between different models we have heard about, or will soon hear about already. So what's the pictorial view for this? We have 2 Gaussians, the red and blue blurbs on 2D that share a covariance matrix. And the class, the posterior probability is simply drawn like this, where the decision boundary somewhere here is linear. And on one side, the red class is more likely. On the other side, the blue class is more likely. So you may say, well, we made a crucial assumption of shared covariance. So if the class conditional probability have different covariances, then the quadratic term will not cancel out. And then we get essentially a quadratic discriminant. So here is an example in the book. It has 3 Gaussian densities. They're not isotropic. The blue one is just the rotated version of red and green. Turns out that the discriminant boundary between the red and green are still aligned, but the boundary between red and blue and red and green and blue are now quadratic curves on 2D. For those of you who remember like geometry or quadratic curves, they look like this, right? So which is to say, for Gaussian conditional probabilities, we can express linear discriminants. We can also use it to express more powerful discriminants. But we don't have direct control of the shape of the discriminant because we care about data likelihood given class. So we just talked about the geometric intuition of class conditional densities but are Gaussians. We haven't talked about how to quote unquote learn them. This is a case where we've specified a model. We haven't talked about the learning. In a lot of machine learning papers, these different stages or different assumptions about how the learning pipeline operates is explicitly spelled out. For some, it's not, it's sort of mangled up, but we need to be able to conceptually tease them apart. Scanning a quick question. Yes, the logic function is the inverse of the sigmoid. Thanks, Kylie. So let's look at the maximum likelihood estimates. So because we, what we want to estimate, the parameter set are actually pi. The class basically pi is, let's say, P of C1. And then P of C2 is 1 minus pi. Naturally, if there are 2 classes, we want to estimate pi, mu1, mu2, and sigma. It's a matrix, right? So these are the set of parameters we should be able to estimate. Because we were talking about this sigma of a alpha function, we want to write out this joint probability of data point and class label. Again, using Bayes' rule, it's basically pi times the Gaussian probability under mean mu1 and the shared covariance, and 1 minus pi times this Gaussian probability of mean mu2 and the shared covariance. If we have n data points where we write the target, again here target is class 1 or class 2 or 1 and 0, under like condition on this set of parameters, we're being a bit Bayesian, it writes out like this. What this expression showed is that in the expressing probabilities for class labels, what we usually do is to multiply the different classes where we raise the class label to the exponent. Right, so what this says is basically T n equals C1 in this case, or T n equals C2. This is what the multiplier and exponentiation does, and we will get very used to it throughout this class, especially this section. Okay, now let's do maximum likelihood. Or we basically want to maximize the log likelihood. But what we do, we stare at this form, right? So this comes out as a sum when we simplify it. And then these different terms are all multiplying each other. So that's very nice. And the Tn term comes to the front. And we essentially have log of pi plus log of this Gaussian probability business, right? And under log, the multiply sign becomes sum again. So we will have 1 minus Tn log of 1 minus pi plus log of this Gaussian, this other Gaussian. Right. So roughly goes like this. And if we would like to estimate pi to start with, notice that pi does not appear in the class conditional probability, including the normals, right? So we just collect these two terms, one here and then one here. And now we have the term that depend on pi, right? And the summation sign is still at the front. This also says that if we want to take the partial derivative of the log likelihood with respect to pi, we just differentiate this with respect to pi. What this gives us is, well, derivative of log of pi is 1 over pi. The summation sign is still there, and we have Tn here, plus 1 minus Tn still stays. Right, apply chain rule and get the -1 on top. We set this derivative to 0, rearrange the terms, we get the MLE estimate of pi to be essentially the sum over Tn over n. Or in other words, it's the fraction of training data that is of class 1. So that's intuitive. It's reassuring. We went through this trouble, expressing the likelihood term, differentiating it, and then we get an intuitive answer. Okay. Now let's look at the other parameters. The MLE solution for the means, let's not try and do it here. Can read a book and yes, amuse yourself, I guess. They are essentially averages of the data points that's within class 1 and class 2 respectively. So this is intuitive. And the covariances are also the weighted average of the covariance of basically data points in class 1 subtracted by its mean. So basically the data covariance in class 1 divided by the number of data points in class 1 and do the same for class 2. So what just happened? If we do MLE for classification under shared variance conditional Gaussian, we essentially, use the weighted averages of data points and their covariances and their counts. They come out as MLE parameters. So that's good. One notable drawback is to say, hey, we want to separate two classes in d dimensions. What we end up with is, okay, so pi is one dimension, or one parameter. Mu1 and mu2 are both sort of d-dimensional vectors, but the covariance matrix is order of d squared, number of parameters, or like d equals 3. the upper or lower diagonal of covariance matrix. So that's lots of degrees of freedom. And when D is large, when we have high dimensional measurements such as social interactions or text, or your, like, let's say the output of a deep neural net has 2048 dimensions, something like that. That could be quite bad, right? So let's pack that thought. And I'm not going to cover naive Bayes here. Let's briefly cover logistic regression, and then we can take questions and then expand on some of these discussions if need to. Let me pause and look at a question. So thanks, Beiyang and Jinhong, for you already answered it. I think it's classification or clustering. So for Vikram's question is, for the covariance matrix, N1 and N2 gets cancelled out. Right. Is it a normalizing scalar? Yes, that's correct. Yes. Somehow the book chose to express S1 and S2 this way because they are sort of the maximum likelihood estimates of the class covariance in class 1, right? For example, here. Right. So what this S term, if you substitute S1, S2 into it, what it corresponds to is just the covariance matrix for the whole data set, except for each training data point, the covariance is taken with respect to its own class mean. If X is in class 1, so we only look at this deviation from mu1 and don't care about how far it is from mu2. So this is we can also look at it. Contrast this with the generic Gaussian covariance estimate where there isn't two different centers. I hope that makes some sense. Because we enforce that the covariance for these two classes are shared, we're essentially averaging. And if there's class imbalance, as we can see that, right, one of the covariance is going to dominate a bit as well. I hope that helps. Shout at me just directly if you still have questions. I think we want to see this part, and maybe we'll skip the derivation or cover the derivation next week, because I think we really care about logistic regression, figuratively and seriously. So we said early on in this class that there are three types of approaches we want to do, right? One is discriminant functions, the other one is discriminative models. We haven't talked about the last one, but why do they both have the word discriminative in their name? Again, the word discriminative does not carry a positive or negative connotation. It's simply sort of a technical term. Because it's focused on learning to separate the classes. So discriminant function learns the boundary. The discriminative models learns the posterior probability, P of C given X, P of class label given X. And what it does is now we're going to have likelihood functions defined through the posterior distribution. So the starting point, we're just spoiling the end here, is we just said the sigma square covariance matrix has d square number of parameters. Can we do without them, right? And then because we're learning the posterior directly, it might be better for prediction. It may be better. So this is hand wavy. We'll see. But the downside, right? So there is no free lunch. What the price we pay is we cannot create a synthetic data using P of C given X directly, because what we can generate from that is only class labels. That's not data. And then there's the quip about asymptotic performance and behavior, which let's not go in there for now. After the generalization lecture, you might know what this is, the style of argument this is going to entail, right? Okay, so we have been talking about linear classification models, but since we've covered basis functions, you should always think of them as we can do this with a basis function, and that gives us very flexible classifiers. And here's an example. Yeah, if we have Gaussian basis functions phi1 and phi2 on this space where there's blue and red classes, plus in the original input space, somehow red classes in center and blue classes in two sides. If we're trying to learn a line, that's bad. But if we have Gaussian discriminant functions that are centered basically here and here, and then we essentially project, measure how far each point are from each of these centers, that gives us another two-dimensional space, right? So it basically says that, well, for phi2, right, so because these Gaussian basis functions, they are large when the points are close to the center. So it's green here. This Gaussian maps to these points. This Gaussian maps to these points, right? So, and this blurb goes here because they are small, right? The values of these blue points, the second group of blue points will be pretty far away from this phi1, this Gaussian, and they all come here. And in this space, we can easily draw a line geometrically to separate the two classes. Well, we just said classes which are not linearly separable in the input space may become linearly separable in the feature space. On the other hand, in here, we're not talking about class overlapping. If we have the blue and red dots sitting on top of each other, as we did in the early decision series slides, if the densities overlap, then nonlinear features, it's worth noting, nonlinear feature map cannot remove the overlap. They don't fix the inherent class confusion. They can only increase it. There's no free lunch when we might actually lose something, loosely speaking. Okay, now let's just directly parameterize this function we've been staring at a few times, right? So it appeared as sigma of A or alpha, right? And now let's just say this, we want to learn A, which is W transpose phi. For good reasons, because we know that if the data were conditional Gaussian with shared variance, it looks like this anyway. And if we're doing this, we will be learning, like, it's the same expression for the posterior estimates, but the linear number of parameters, because is d dimensions rather than quadratic d squared dimension, or d squared over 2 roughly. Another note about names. So the statisticians confuse us. They have a long history, and probably there was a good reason to call it logistic regression. Logistic function, applied to a regression function W transpose phi. But for machine learning purposes, this is, I would say, a separating point. For people who know, like, anything under the hood of machine learning than not, because it's a model for classification, it's not a regression model. yes, as we said, it's the same expression as the conditional Gaussian model, right? So this is our model definition. This is what logistic regression is. So we would like now to learn it. And the criteria for learning is maximum likelihood. So as usual, we try and write out a likelihood function. Basically, right now, we write out a likelihood function of class label condition on the weights and data, right? Where the class label are observed data points, and these y's are the logistic decision functions, right? We already saw this multiplying exponentiating trick. Again, this means Tn equals 1 or Tn equals 0. And the take-home message for this slide is essentially the negative log likelihood function results in the cross-entropy error function. To see this, we basically take this term, put a log in front of it, and we want to maximizing log likelihood, and then we also want to be minimizing this error function, which is the negative log likelihood. We did this thing we did a few slides ago. We pull the exponent to the front and take log of y. And for those of you who have played with neural nets, this is the cross-entropy log error function. And you can also take the gradient of this cross-entropy error function, which I haven't changed. It basically just copied on this page from the last page, and use these definitions and the properties of this logistic function to derive the gradients. I know we're just at an hour and a half. We can walk this through if you want me to in the Q&A, but basically this is what it involves. You just take it apart, plug in the use chain rule, plug in the derivative, right? So let's just end or conclude with a brief critique of logistic regression. So I would say logistic regression model is very good and robust. So much so that it's very tolerant on linearly dependent feature vectors. And it can handle, when we say linear number of parameters is good, what we really mean is that it's very robust in practice. You can have like D feature dimension, input dimensions, D in millions, and sometimes even billions. Right, so I remember around like the early 2010s or late 2009 or so, there was a bunch of colleagues who worked in Facebook, and their prediction or their one version of the best performing newsfeed recommendation was essentially to treat every single digital item that has ever posted on Facebook as one of these dimensions. And then run logistic regression. So this is also to say that the input can be very sparse, and logistic regression can learn with lots of data and in very high dimensions. But one criticism is that if the data is in fact linearly separable, right? So because we say P of C1, let's say given X is sigma of W transpose X, right? If the data is linearly separable, then there are infinitely many hyperplanes that separates these classes. So the colored ones are just a few examples. Logistic regression will actually not be able to distinguish which one of these hyperplanes are good. Again, this inspires Bayesian approaches, SVM, and many other approaches. So there's that. But in fact, if you find a job as a data scientist and you find yourself trying to solve a classification algorithm, apply this real life machine learning practice master algorithm. Look at your task. If there's already data and feature given to you, great. If not, extract some, represent your labels, and then try logistic regression. If it works, your job is done. And regularize it a bit as well, right? Try tune your regularization parameters properly. If it fails, then maybe design a fancy algorithm. Or try and reduce your problem to logistic regression again by changing the representation or changing the data representation and so on. So this picture does not include like considerations on how good your optimization is, because in logistic regression you can do SGD. The slide we just skipped of derivation. We didn't quite cover what decision you make, like the non-trivial decision theory paths, the learning bounds or evaluation settings, and so on. But yes, we like logistic regression. So this is what we covered today. We covered classification, decision series, 3 modes of learning classifications, discriminant functions, generative models, and probabilistic discriminative models. I'll skip some details, which I argue are less than crucial, but you are expected to be able to do maximum likelihood estimates at this point after so many different iterations. You get plenty of practice, and in the assignments, yeah, for sure. And then we also skipped over what's called approximate inference, Laplace approximation, and Bayesian logistic regression. So we'll do that when we cover approximate inference in general towards the end of the semester. That's it. Is there any questions? Okay, let me scan the chat log again. Fei Yang asked, so the joint distribution of C and X is generative? Good question. Right, so it's a terminology. Let me say that in the scope of this class, and the chunk of machine literature around that, the time of the book or just precedes it. Let me see. Right. So let's go back to this one of these generative model slides. When we say it's generative, it does mean that you can use this model to generate some data. And usually it's only the class conditional probability X given C that allows us to generate data, not the join. Working with the join to sample or generate data is very hard. I hope that helps a little bit. So this point is, I think will be clearer when we get to graphical models and latent variable. Because I have said that you guys should read Gaussian mixture models this week, because we'll use it on Wednesday. Like with a Gaussian mixture model, given the mixture component, we can generate data, but we cannot generate from the joint distribution, which is this sort of multi-bulb, like complex shape. I hope that's informative somehow. So Fei Yang, you could let me know while other people think about their questions, if any. Again, I think, so here's my high-level takeaway. This part of this particular lecture is somewhat technical. I don't think they're particularly difficult or new bits. Like most of the math is in MLE, which you've seen a lot of times. But I hope what you will walk away is more comfort with maximum likelihood estimates, but also the overarching logic on how here are the different ways of thinking about classification. Here's where least square breaks. And here's logistic regression. Like we just keep getting it. I hope that helps. And people don't seem to have questions, so that means you got all of it, which I'm certainly happy about. Oh, I just wanted to maybe say that this bit of derivation on the gradient of logistic regression, the end is very simple. The process is somewhat like you can see that it took me a page, and the book doesn't have it. So if you don't know, yeah, if you get confused, hopefully this slide helps you. Or you can, I guess, test your familiarity with like taking gradients and chain rule by trying to fill it in here. All right. Okay, Jinhong asks, yes, let's just, yes, because we have been looking at these quantities, x given c, c given x, a few times, discriminative model does refer to where the main, or I guess the central object for modeling is this probability of c given x. It's called discriminative because, well, right. So let's just use this slide to illustrate this. I'm gonna use, okay, I haven't used blue. Let's just use blue lines. So when we did generative model with one Gaussian per class, what we said is we care about P of C given X, but what we actually model is P of X given C. We assume this is Gaussian. And then because we're using Bayes rule, we need P of C anyway. So this is a number. Right. And in discriminative modeling, we care about P of C given X, phi is X, we already know that. And we directly model it as this logistic function applied to a linear projection of phi. Okay, so sneakily, what this implies is, okay, we ignore P of C. We also ignore like the exact shape of P of X given C, let's say. So what this means, this can mean two things, right? So when we ignore P of C, so this like when if your training data is imbalanced, you need to really think about what loss function we're using, right? Because the loss function, right, so this loss function, it does not, right, so this is assumes every data point counts as the same. So if you're using logistic regression to classify a cancer patient data set, yeah, you might have some problem here. If you're using logistic regression to classify some rare event, like this will have some implicit implications on what your classifier would behave. It will basically count the majority, weigh the majority class quite a lot, right? Back to decision theory, so they're applied here. And in terms of ignoring the shape of P of X given C, going back to the picture we had quite early on in this lecture, this one, so let me just annotate. So if we learn a generative model, we might have the picture on the left, and we know like the interesting shape of X somewhere. And then if we learn a discriminative model, we get the picture on the right. So either this, I guess, multiple modes in X is uninteresting or unuseful. But anyway, we don't know it. And as you can see, if we have this kind of a double bump or a single hump Gaussians, we can easily generate the data. If we just have this, we can't. Okay. Right. Fei Yang again. Does cross entropy here mean cross entropy or for joint Bernoulli distributions? Right. Okay, let's go there. Yes. So here, the cross entropy term here. So as we said last Wednesday, entropy is, well, basically P times log P, summed over the data, well, the sample space and put the negative in front. Right, so cross entropy is basically P times the different log of P. And the cross entropy is 0 and 0, 1. These two distributions are the same. So therefore, yeah, so here it's essentially measuring the discrepancy between the TNs and YNs, and that is what we want. And yes, here the TNs and YNs are 0 and 1, so they are considered Bernoulli, but but not with a uniform probability though, right? Because Yn is this sigmoid function, so you can think of the output of sigmoid function as the bias of the coin that we're flipping. I hope that makes some sense. And let me just say that this is a good question, which also serves as evidence on why we were talking about information theory and why it's like this is one instance of information entropy being useful in constructing loss functions and or being a component, or in this case, the entirety of a loss function. We'll see more of it. Actually, on Wednesday, we're going to see KL divergence in the EM thingy. Okay. So just Jinhong and Fei Yang going alternatively. Take this one, conditional probability. I think the X given C is intuitively generative as you could sample. Yes. Could you please explain more about why it wouldn't be appropriate to just sample from the joint to generate new data? Right. Can we just randomly sample some X with some random class labels? That's a good question. Yeah, I argue you cannot. Right, because, so what is interesting here? Let's go back to this picture. What's interesting here, and what we're trying to learn is the dependency, the goal of learning, the high level goal of learning. Of learning in here is assuming X is, say, one-dimensional, or there's actually inherent structures in X as well, but let's just not overcomplicate things, is the often non-trivial dependency between X and C as reflected in their joint probabilities. Which means, right, you ask if we can just sample the joint probability of X and C. So, for example, in this picture, assuming we have a prior that properly scales these two blue and red distribution, we can indeed combine them to form a joint distribution and sample And here in this picture, if we combine these, right, we'll get P of X, sample from P of X, but we still need to get C. Or we can first sample C, then sample X from the conditional distribution of X given C. So I argue in here, there are two things. Let me try and draw some P of X to try and make the point. So from here onwards, go back. Why does it allow me to draw that looking distribution? Okay, so from here onwards, the joint is going to look different, and then it's gonna go back and look like the red again. So let's say this is P of X. Right. So if you want to directly sample from the joint and still respecting these dependencies, which I argue is important, you have two ways. One is to first sample class label C, and then sample conditional C from the blue and red distribution, which I argue is a lot easier than let's say we sample from P of X, like this yellow line that I sort of scribbled here. How to sample that is another sort of non-trivial exercise because of the multimodal nature of this complex distribution. We'll cover in the sampling lecture, which we may or may not include this year. Let me say, make no promises, but just know that's non-trivial. Assuming you can sample P of X using stuff like rejection sampling, importance sampling, and stuff like that. And also when we do rejection sampling, right? So estimating an estimation of a function from that is quite reliable. Individual samples, you might need to go through lots of raw samples to get to one. Okay, assume you can still do that. Then let's say, if we sample P of X, then we need to now sample P of C given X. Right, so that requires us to know the posterior probability function. Right, so usually that means we should have already done the learning. And so I guess my argument is that so to generate data, right? So this is way number 2, way number 1. Oh, okay. Let me spell out on the page what we're trying to do here. Basically, we want tuples of X and T. Right, where these are class label C1 versus or C2. The way number 1 is to sample C first, and then sample X according to probability of X given C. Right. So I guess I argue that I strongly prefer this one for the kind of distributions we're staring on the screen. Because concretely, right? So sampling P of X from this complicated looking like data marginal distribution is doing as much work and often more work than just sampling from like the class conditional X given C. So, and sampling C1 and C2 are trivial. Doing the other way around is quite hard. I hope. Yes, Jinhong, yes, it's generally possible, but yeah, it's difficult to work with. I hope that helps. So that's pretty much it. We have followed pretty close to script of the book, although I did not feel that the book teases out these, right, so what do these expressions mean as much. It has many interesting like discussions. For example, when would legislation not, like it does not distinguish among the different separating hyperplanes. I feel this book in general, well, to my personal taste, it does not prompt us to think about the whole picture of using machine learning, like how we design the whole machine learning pipeline, and how to critically think about different components, which I'm trying to sort of supplement a bit. Usually, the assumption of most machine learning textbooks is that if you can think about the math, you should have enough critical thinking ability to figure out everything else on yourself, like the sensible choices of validation, how to interpret, how to debug the model, which, as we find out in doing research project, it's an acquired skill, which I think the assumption of where if you can do the math, you can do them is true, but it does require. With that, I think I'll say bye for today. We've gone on long enough, and our recording have also been rolling the whole time. So there's that. Bye, everyone. Let me stop the recording.